Okay, so we are going to talk about intercanister calls, how to call other canisters. This is essential to building on the IC. The vision is to have a system where you can easily interact with other applications. So you have a canister for OpenChat, you have a canister for the Motoko Bootcamp DAO, you have a canister for every token, and essentially we need to be able to call multiple canisters. For example, a marketplace would need to be able to call all the canisters for every NFT collection that they use. DeFi exchange would need to work with a lot of token canisters and so on. So you've understood that this is essential, and doing intercanister call is something that is the main task of the ICP developer, I would say. Well, one of the main tasks. So here I have two canisters in my source folder. I have canister 1, canister 2, and I have this dfx.json where I've defined my two canisters, so canister 1, canister 2. Canister 1 is going to be very simple. It's just a secret canister that stores a secret message that is here. And this secret message can be accessed through a query function, and it can be modified to an update through an update function. So this is something we've already seen quite a few times, just a simple canister that stores a message. Canister 2 is a little bit more involved. We can do more things with it. So essentially we have a system of invoice. An invoice has an ID and a field paid, so the invoice can be paid or not. We have a buffer that stores all our invoices. And then we have several functions for this canister. We have a function to create invoice, pay invoice, and then we have functions to get the secrets. So essentially, our users are going to be interactive with our canister 2. The canister 2 will be calling the canister 1 to get the secret. And that's how we essentially build our application. This is a example. I'm not saying this is a good way to do it. I just want to show you how to do intercanister calls, but this is I would say, silly example for today. Yes, the recordings are already published. And there is actually, if someone can share the links to have the recordings in the chat, that would be great. I have published all the recording except the one from this morning and this one, which I'll be doing tonight. So essentially the idea is that only people that have paid our invoices can access the secrets. So the user is going to call the canister in a first time to access the secret. If there is no invoice for this user, then for this ID, then the canister will create an invoice. If there is an invoice, if the invoice is paid, then we will share the secret by calling the canister 1. If there is an invoice but it's not paid, we wait for the user to pay the invoice. We don't involve any real token because paying is really just calling the paying function and declaring it as paid. So it's not really, there is no really any monetary value that is moving around here. It's simply just an example. Okay, so yeah, maybe first I will show you how you would do it. So we have the canister 1, which is actually defined in the canister 2. So it's just a variable inside our code. And this is as easy as this to import another canister in your code. This is called actor declaration. So importing an actor by declaration. Essentially, what we do is that we define a name for our variable. So that would be canister 1 here. Then you specify the type. So our type is actor and then the interface. Now it should make sense. We have this actor bracket and we are reusing it because this time we are defining another canister. And then we need to specify actor and the canister ID of the canister that we are trying to call. So this is the ID here. I can copy paste here. Now you might be saying something if you followed the code of canister 1. So this is canister 1 on the right and canister 2 on the left. Why? So yeah, I can remove one of those declaration. We just need one. Why are we only specifying the get message function when we have two functions for this actor actually? So this is something to keep in mind, is that when you declare a canister, you only need to specify the functions that you are planning to call. So in that case, I'm not planning to call set message, at least not for now. I'm just planning to call get message. And so in my canister declaration, in my actor declaration here, I can omit the functions that I don't want to call. And so I just specify get message. Make sure that this function is following the same types as the function that you are planning to call. For example, if you have a NAT here, it's going to crash and it's going to cause a lot of issues. So make sure that you respect the interface, the declaration, interface declaration of the canister that you are trying to call. And then how do you know the canister ID of this canister? Well, you need to know this information. So in our case, it's a little bit annoying because we actually don't really know until we have deployed. So here we would need to deploy canister 1 first. So dfx playground canister 1, because we need the ID of canister 1 in canister 2 to actually be able to call it. So I have this ID, but this ID is from a previous example, and I'm not sure it's going to be the same. Yeah, no, it's gonna be a different one. So this is the new one. And now I should be able to deploy canister 2. Well, I have some. Does a canister always have the same ID? No. So, I mean, the canister ID is a container for your application. So when you deploy on the IC, like you have a dedicated canister ID, it's always going to be the same when you redeploy new code. You still have this canister ID. But if you are working like locally and you're just trying out your code, your ID will change every time. For example, every time we deploy on the playground, if you've noticed, we have a different ID. Yeah, it depends. Like if it's your canister, you have paid for it, and it's like an application that you have deployed in production, you can redeploy and you can keep this ID forever as long as you pay. But when we are doing locally, every time we deploy, we have a new ID. At least every time we start our replica, we have a new ID. And on the playground, it depends. Like you have 20 minutes. If you redeploy within the 20 minutes, you are going to redeploy in the same canister ID. After the 20 minutes, it's going to be a new ID that you have. Okay, so we are ready to call and test our methods. Now, where is the intercanister call? It's here. So you see that when I call this getSecret method, so this is canister 2, I check my invoices. So if there is no invoice, we return an error. If there is an invoice and the invoice is paid, then we return OK, and then await getSecret. Await getSecret is just a method that returns the secret by calling canister 1. To call a canister, you simply need to do canister, like the name of your variable. So in my case, canister 1, dot the method that you want to call, so get message. And this is where the await comes into place, because remember that every public function, at least the public function of the actor, so the one that you are able to call, they are asynchronous. So you need to await on it. So this will take more time because you actually have to await. You will notice that this function has a higher delay than other function. So let's try it out. I'll open the Candid UI. And okay, so this is canister 1. I will need canister 2. So I need to first create an invoice. Okay, my ID is 0. It's not paid yet. I'm going to pay it. So I just call pay invoice. My invoice is paid, and now I can get the secrets if I call get secret. Notice that it takes more time. You can see 3 seconds, and you can see this message that appears, and this message comes from the canister 2. So canister 1, so it's here. So we have successfully made our first intercanister call. We have gotten a variable that was stored in the canister 1, sorry, inside the code of canister 2. And you could do that with variables, but you could do that with functions. You can call update function, query function, it doesn't matter. Now, something to keep in mind is that you cannot call intercanister call when you have a query function. So if you try to do like a query function, let's say public query func example, and you would try to do await canister 1 dot get message. So you try to call intercanister call through a query function, it doesn't work. Misplace await, send capability required but not available, cannot call a shared function from a query function. So it's only through updates that you are able to do intercanister call. I won't go into it today, but there is something called composite queries. Composite queries essentially enables you to call other composite query. So essentially a query method can call other composite query methods, and you can actually gather information across multiple canisters, but you cannot perform any modification because remember that this is a query function. So now that's how you do a call to a canister that you know, because here we have access to the code and we have access to the source code and the canister ID. This is our canister, so it's pretty easy to do. How do you do a call to a canister that you don't own? How do you do that? This gets a little bit more complex. So you would need to essentially have the interface of this canister. Even if you don't have access to the code, you at least need to have the interface. And for this example, I'm going to try to call the ICP canister. So ICP is a token, and there is a canister, which is the ICP ledger, which runs on the IC and stores the balances of everyone and also manage the transfers and everything. And so if I take a look at this canister ID, this is the canister ID of the ICP ledger. If I take a look at the ICP dashboard, you can search for canisters and you can access canister that have published their interface. So this one is a canister that has published his interface. And you can see, so the controllers, the ICP ledger is controlled by another canister, which is the NNS root canister, in case we need to upgrade it. You can see the subnet ID. So this is the subnet that stores the ICP ledger. And you can see the module hash, which is the hash, the SHA-256 hash of the WASM module. So essentially it's a random string that gives us information, enables us to verify that the code running on the ICP ledger is the code that claims to be inside this canister. And now we have all the methods, so we can see query, 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 update. We have quite a few methods. And at the bottom of this canister interface, we have this section. And we have the interface for this canister in different languages. So Candid, Motoko, Rust, JavaScript, TypeScript. This is super useful because we need to use that to call the ICP canister. So you can see that if you scroll down, at the end, you have access to this public type self, which actually represents the canister itself. So you can see all the methods, ICRC1 balance, ICRC1 decimals, ICRC1 fees. So those are the methods that we find here. And of course, you have access to, well, the complete list of all the methods that you could call. Then all those types are the types that are used inside the canister. So those are custom types that have been defined. And you would need to import them if you wanted to interact with this ICP ledger canister. In our case, I just want to interact with a simple method, which is going to be ICP canister symbol method, which returns a symbol. A symbol is this one. So we want to call this one, which returns the symbol of the token, which is, well, of course, ICP. But we want to do it from our canister, not from the Candid UI, from this UI. And if I take a look at the types, I have this type symbol, which is an object which contains only one field, symbol of type text. So I can copy paste this. Actually, I already have it, as you can see here. And then I need to go to the method and see this is the method that I want to call symbol, which essentially is a query method that returns just a symbol. So it's a very simple method. I have defined it here. Again, this canister has like, I don't know, 20 methods at least, but I'm only using one here. So I just need to specify one. Then the canister ID. So this is the canister ID of the ICP token. And then I can use it simply by doing await ICP canister dot symbol. And yeah, I need to, well, of course, I'm getting the symbol field from the symbol object. So let's try it out. Actually, it's already deployed, so we can check canister 2. No, we didn't. Yeah, we still don't have it, so I need to redeploy. Okay, so I get the symbol here. And you can see it's taking some time because it's an intercanister call. So as you can see, I received the answer, and I can tell you for sure that this canister is not in the same subnet. So you can call canisters from other subnets, but it adds some delay because when you do that, you have to do 2 consensus rounds. So it adds some latency, and you have to take that into account when you do intercanister call. So like 11 seconds here, I guess the playground is a subnet, actually is inside a subnet, and the ICP ledger is inside another subnet. In our case, with the previous canisters, it was faster because it was in the same subnet. So yeah, it's around 10 seconds, 11 seconds. Any questions so far? How did you get the idea of the ICP canister? Oh, there is a question which to get the ID, I simply found it on the documentation. It's a public, I would say, ID because this is like a canister that is known. In case you don't know the ID of the canister that you want to call, you would need to either ask the developers or find a way to find the canister ID. Why has the declaration of the function of canister 1 in canister 2 a shared, but in the original declaration just public query, not public shared query? So a shared method is a method that can be called by other canisters, and a public method is a method that is public, so it can be called by other canisters and other users. There is no difference between public and public shared, at least in the actor part of your code. So when you have a module like utilities, you have utilities function, you are going to have a module. Then maybe you have a public function, print, I don't know, print something. So you're going to import this module. This is a utility module, so it's not a canister, it's important to understand the difference. Here you have an actor, here you have a module. And so with the module, it's a code that you can use in your actor code. You can import it. So we could do it like import utils. Oops. And we would do like this. And then we could use utils.debug like this. I guess it's print. Yeah, I cannot use that directly in my code, but I could use that here. Okay, it's good. So public is a keyword that can be used also during like inside of modules, you know? This is public, and if I have a private function, then I cannot import that in my canister, like in the rest of the code. So if I try to do utils.print2, it's going to say that it doesn't exist. Field print2 does not exist because it's not defined as public. So public is a keyword that we use both in the actor and in the modules to define something that we can import on the outside of either the actor or the module. Shared is only for the public function inside the actor. So here we could do public shared, but you don't have to do it because by default, it's something that is already known. Like it has to be shared. If it's public and it's inside an actor, it's going to be a shared method. The only case, and don't ask me why, I don't know exactly why, and I think there is no specific reason. It's only like syntax reasons. When you want to access the color, you remember when you wanted to access the color, you needed to have this shared. If you don't have the shared, you don't have access to the color. And it was like this public shared color. And here you have access to the color. So to sum it up, it's not like you don't have to worry about this distinction between shared and not shared. Actually, here I could also just remove the shared and it would still work. Do you think one day ICP subnets will be instantaneous communicators, much like current centralized internet? Nothing is impossible, but it would require quite some work on the protocol side of things. So very hard and very long work. I mean, nothing is impossible and it would be amazing, but I think it's still a long way ahead. But there are quite a few ways to reduce the latency that I think would be worked on before. So maybe not instantaneous, but at least faster than what we currently have. Okay, so that's the first part of the talk was about intercanister call. The second part is about errors. So I will go and open. I have the errors example here. And also there is a good it was in the training. Chapter 9. Okay, handling errors. So when we say an error in Motoko, actually, for me, was confusing in the beginning because there are actually different types of errors and they don't belong to the same category. Some of them are more like, I would say, fatal errors, and others are just normal errors that are part of the flow of the code. So I have divided the errors in 3 categories to make it like easier for today. We have the errors from the result type. So those ones we have already seen a little bit with, this type OK and this type error. This one is the one that we use the most, but it's also the one where the error is not too bad because it's actually something that we handle and we propagate the error, and it's in the execution of the canister code. It's not outside of the runtime, or it's not something that is fatal. Like dividing by 0, for example, would be a much, much harder error. The second one, well, it's the third in the list, but let's talk about this first, is the trap. So this one we have seen actually a little bit as well, the trap, which can happen in the pre-upgrade, if you remember. Trapping is much more fatal because trapping is getting outside of the code of your canister, because you trap in every situation that your code cannot handle. So essentially your code is running and it's run into a situation where it cannot run anymore and it just exits. And then it's an error that is, I would say, handled at the replica, so on the IC protocol itself, but not in the canister code. So it's much, much like harder to debug. Important to know that if you're calling a canister and it's trapping, then the message that you've sent, like you've called a function, it's trapping. The message is the function is immediately exited. Sorry, it's just getting out of it. It doesn't mean that the canister cannot be used, so you can still call other methods after it has trapped. But there are some exceptions and some cases that we will talk about today. So this is the second type of error. And the second one is the error from the error library, but actually, so let's just, sorry, I wanted to note something. The third type of error is the error that can be handled with the error library, and I will show you what is the error library. Actually, the type of error 2 and error 3 are very much related. The error library is here to help you deal with trap when you are calling another canister and this canister is trapping. So a few more examples of how we could trap in case it's not very clear. There are many examples, but the most common one would be division by 0. Index out of bound. So if you try to look inside the array and you are like index 25 and the array is only 10 items long, you would essentially trap your canister. Assertion failure, so assert false is a very common way to trap. And you can also use the debug library, which has debug.trap, which enables you to trap and also pass a message to the trap. So this one provides an error message. Let's go inside the code. I will talk about the error library and the trap. I won't talk about the result because the result you can read here if you want more information, but we have already talked a lot about it, and we have already seen quite a few examples in our project. We will also see it today and tomorrow. The result type, you should really use it as much as possible because it's allowing other developers to handle your errors. And also one pattern that is really common on the IC, it's to define an error type with a variant. So essentially you have your result, and for the error part of your result, you define a variant with all the different expected errors. And so that enables other developers to consume this variant to do switch case on all possible types of errors. And it's just great for everyone because it means that every possible error will be handled by the code. And that's what we want. Okay, now what is this module useful for. So this module called error, it seems a little bit like strange when you read it. Like you don't really understand why would I use this error if I already have the result type. So this is for handling asynchronous errors. Essentially, let me show you. So let's remove that. Well, first, I would like to just talk a little bit more about trap. I think we need to talk a little bit more about what can happen in trap in asynchronous context. So let's say I have a counter and I have a function increment counter. Which the goal of this method is to increment the counter, as you've guessed. And I have this private function that trap. And for some reason, I'm calling this method here. And then I'm returning. Then I will need a query function to get the counter. And this method will, simply return our counter. So let's deploy our canister. This one is called counter. So let's deploy our counter. What do you think would be the value of the counter when I call, so when I go to this candid interface and I call increment counter, it's going to trap. So it's telling me assertion failed at line 7. Well, it's kind of wrong on the line, but well, it's telling me that it's trapping. But before the trap, we have actually incremented the counter. So if we follow the logic, because we have already incremented the counter, we should see a counter incremented to 1. And you will see that if I call it, we are actually at 0. So what is happening here? There is something called commit points. And commit points are essentially points in the code where all the changes in your state are committed. A commit points can be, this is a commit point. So if we would reach the return of the function, the state would be committed. Another commit point would be intercanister call, as you will see in a few moments. And whenever you have a trap, the state of the canister is rollback. So it's actually getting back to the previous states at the previous commit point. And here the previous commit point is actually before we have even executed this function. So it's going back to the previous commit point. If I do something which is, let's say I have this. So I have a second canister, which is called the trap canister. Maybe I will do something like just a foo function that does nothing, but I just need a function that doesn't do anything. If here I call awaits foo, well, trap canister.foo, it's not going to trap. It's just this one is, we can forget about this one. We just need the intercanister call. We need to trap. We can remove that. And we do an intercanister call. Well, we increment the counter by 1. We do an intercanister call. Then we increment the counter by 1 again, and then we trap. This is going to be interesting. So fx deploy playground counter, and I also, well, I'm going to deploy the 2 canisters that I have. Okay, so let's call our increment counter. So our counter is at 0 currently. We call increment counter. So we increment the counter, we intercanister call, we increment the counter, we trap, and we return. As I've said, this is a commit point. And this is the second commit point. So here, the counter is to 1, which actually makes a lot of sense because we have incremented. Then we have an intercanister call. An intercanister call is a commit point. So here the state is committed. Then we basically pause the execution of this line until the second canister has returned from the foo function. So it calls the foo function, returns the result, and whenever the result is returned, we sum up the execution of the code. So we start again from here. We do counter plus 1, then we trap, but we haven't had any commit points. So we actually trap, so the state is rolled back to the previous commit point, which was here. So this counter is not actually counted. And yeah, that's essentially one of the main issue with trapping and asynchronous calls. So when you are dealing with asynchronous environments and you have to trap, or you trap because you don't necessarily, you have something wrong in your code, you can run into all sorts of issues. This is a simple example, but you can quickly imagine if you have multiple calls, how quickly it can become messy and how quickly you can make mistakes. So for example, one mistake would be to maybe do like a transfer of a token and some kind of error happen, and then you don't transfer back the token. You are blocked in a like middle states, like temporary states, and the funds are stuck somewhere. This is something that could happen, or some other kinds of asynchronous issue. The good news is that there is a good way to handle trap, but only for other canisters that trap. So now, let me show you something. Because right now, the trap was happening in your code, like in the canister that we run. What if the trap happens through the other canister? So essentially, we are doing an intercanister call, and the canister that we are calling, something is wrong, it's trapping. Let's see what happens if we don't handle any error. Yeah, the trap canister has a trap method just in case. Actually, I need to remove the comments. This canister has a trap method that traps. Now, if I call the increment counter, it's telling me, oh, yes, actually, this canister ID is not correct. Wait, how did it work before? How could it even work before? Does not make any sense. It's very strange. So this canister ID should be this one. Essentially, it's telling me that it didn't find the canister that I was trying to call. Okay, now let's try again. Increment counter. Canister, and so the canister ID trapped explicitly, assertion failed. this is where things got wrong. And so here, our counter is still 1 because even if we trapped here, the commit points happens before the canister is actually being called. So we still have the commit point even if the call is not correct. Now we can handle the trap by using try-catch. So if you are familiar with the try-catch in other languages, this is how you would use it in Motoko. Essentially, if you catch an error, you can, we could do like, let's return a text here. We could return this one. So try, then you do your intercanister call and then catch. And so the catch block will be executed whenever this trap. It can also be executed if there is another problem, like for example, the canister is out of cycle, like you're calling canister that is running out of cycles, cannot answer back, or you're calling a method that doesn't exist, all sorts of things that could happen. So yeah, let's go back to our example here. We have catched the error, so you can see that we are executing this block. And then we have error.message, which is a function from the error library, which enables us to print a message from the error object. And so the error that we have is that this canister trapped explicitly, assertion failed, line 4. This is this one, essentially. So this is how you would handle trap from other canister. Unfortunately, you cannot handle trap from your own canister because there is no way to, it would be against the definition of a trap. A trap is basically any situation where your canister code is not able to handle the execution of the code, so it has to trap. So you cannot have any prevention mechanism. I mean, you can, of course, if your code is safe, secure, and audited, and it's clean, you shouldn't be trapping anywhere, but it can happen sometimes when you don't realize it. But at least you can handle the trap of other canisters. Also, you could use this. I haven't seen too much use case. I mean, I've seen some use cases, but you could also just throwing an error instead of trapping. So if you know that your canister will be consumed by someone and you know that some situation should never happen, you could use error.reject, which would be a way to indicate to the consumer that something is wrong. And you can specify the message. So instead of having a message that is like the message that we have here, which is like a message that is from the IC, so it's like a default message, we could have a custom message. So like, so if I do that, I can see my custom, I should be able to see my custom error message. Hey, this is a custom error. And that's it. That's all I have to say right now about errors. Now, I guess the next step for you is just to, code, and you will probably have your own errors that appear, but it should fit within one of those categories, either an error that is handled by your canister or not handled by your canister. And if it's handled, you can use result. If it's not handled, you have to deal with trap. You have to be careful with any asynchronous call that you would make and all sorts of consideration. No question. So I will finish this session here. We have the next one in 1 hour and 15 minutes. You can start the project number 3 already. and I see you there. And goodbye.